So we are dealing with the fifth problem in this series, and the fifth problem is stating a thin wire ring of radius r has an electric charge q. What will be the increment of the force stretching the wire if a point charge q naught is placed at the ring center? So if we approach this problem, we begin by drawing a diagram for the situation which we are going to discuss, and for that we are considering a diagram like this. Now the charge is distributed over the entire length of this ring. So the charge is distributed throughout the ring. The charge is equal to q and the radius is given to us as small r. So due to the charge which is already given to the ring is already in a stretched position because of the repulsion between the charges which is given to the ring. And now a charge is placed at the center of the ring which is equal to q naught. Now due to the repulsion between the charges on the ring and this charge q naught, an additional force will come into play. So over here we can consider a small patch which we are taking here, a very small patch. And if we consider the forces on this small patch, so we begin by drawing a line over here which is joining these two charge. So we consider something like this. So this is what we intend to consider. So this is the first line that we draw. And this one is the second line which we consider. So we begin by considering a elemental charge over here on the circumference of the charge which we have drawn. So although I am drawing it a little big, but it should be kept in mind that what we are considering is a very small length of charge which is subtending a very small angle at the center, and the total angle which we are considering is delta theta, which is divided into two aspects, each angle being equal to delta theta by 2. And due to this interaction, an additional force that comes into act is T. This additional force that comes into act is T, and if we break the component of this force, then we get this component as T sine of delta theta by 2, T sine of delta theta by 2. The cos component will cancel each other in both the directions, and the T sine delta theta by 2 is balancing the electrostatic force which exists between the point charge q naught and the elemental charge over here. So the next aspect that we discuss is what is the charge that we have on this surface. So for that we write lambda equals charge per unit length, which is equal to 2 pi r, and this is equal to dq upon the length of this part which we are taking as delta L. So delta L can be written as, using the fact that angle equal to the angle delta theta, arc length upon radius. So arc length upon radius, so we write delta L is equal to r delta theta. So from here we have charge dq, and dq being equal to q delta theta upon 2 pi. And to calculate this additional tension which is generated inside this wire or the ring, we say 2t sine of delta theta by 2 is equal to the electrostatic force which is repelling the wire in the outward direction, and delta theta being very small. So if delta theta is very small, then we can write it as 2t delta theta by 2 is equal to k, that is 1 upon 4 pi epsilon naught q, and the charge on the elemental patch, this is charge q naught which is centrally placed, q delta theta upon 2 pi. So this is the value that we obtain. So now the problem is asked us to calculate the additional force which will act. So the additional force which it will be subjected to, T, is equal to q naught upon 8 pi square epsilon naught, and obviously the separation between them r square, so kqqq by r square, and this is the final answer for this problem which we have discussed.